Okay, so we will start today with Newtonian mechanics. And right away, we will discuss some of the basic ideas which are needed to formalize the definitions that we will be understood later on. So the basic assumptions that Newton took. Let's first talk about the idea of continuous space and time. And there was this Zeno guy in 500 BC or 600 BC, somewhere at that time, and he said that he ridiculed this idea because his argument was something like, if you have, let's say, an arrow, and if you want to throw it, and let's say it comes at this point and it wants to now move to this point, right? This is your starting point, this is your end point. And the idea of continuous variable, this is like a continuous variable. The idea of continuous variable can be well understood by just looking at the real line. So you have this set of real numbers here, okay, set of reals. So you have this 0 and this infinity and this negative infinity, and the idea of continuous variable is, let's say you have any point 0 and you have any point 1. So let's say this. So between these 2 points, you have an infinite number of numbers, right? So it's like set of reals are made up of rationals plus irrationals, and due to that, there are infinite number of points in between these 2 points, right? And this is the idea of continuous variables, that there is no gap between any 2 points. There is no gap, there are infinite number of points. Okay, so he said that if you have an infinite number of points between each 2 points, then you will have to traverse an infinite distance, right? And he said that no matter what your speed is, it would take you infinite time. So for an observer, let's say outside here, and he is watching this arrow, this is some kind of watcher, and this guy watches and he says that, okay, when I look at this arrow, what I see is it's not moving at all. There is no moving. Okay, there's no motion. So what he says that if you are going to take infinite time, that then every point will be, at each point of time, you will look like you are at rest, you are stationary. So he said that if continuous time and space are taken, then motion is ill-defined. Motion can be defined. It's just that you can't take continuous space and time. Okay, so this was the argument of Zeno, and to counteract this, actually, there is a very simple solution to it, and you can get it in differential calculus, but we will go through a different route, and we will see how it comes about. Actually, the idea of Zeno is directly the idea that if you have infinite series of numbers, they can't possibly converge. They will have to diverge. They would diverge, right? This was the idea, that if you have infinite number of numbers and if you add them up, then it has to diverge. It goes to infinity, right? It can't possibly converge. And by convergence, I mean that if you have infinite number of points and you add them all up, you get some finite number. Okay, this is the idea of convergence. Okay, so if this is so, then what is happening? It's actually a very simple argument. Let's say you have this point and this point, and it defines a distance of 1 unit. And I have this guy which is willing to move a lot, and I'm guiding him that each step that you take has to be half of your last step, right? Half of your last step. So in the way, like, you take this much of step, then you take a little less, then you take even a little less, then you take less, and you are, in theory, according to Zeno, he should never reach this end point. It would take infinite time for him. Let's see how it goes. So let's say your initial distance to be traversed was 1 unit, then the initial step is like half of that 1 unit. Then the next step is even half of that, that is like 1/4, and the next step is even half, that is like 1/8, and you have this infinite series, right? And what you get, this is your sum. Okay, and you right away see that this is like a geometric progression, and the convention of this series is like this, right? The way in which you write it. So it's like 1/2 raised to n, and from 1 to infinity, right? And you see this is a geometric progression. Okay, and the first term is like 1/2, and the common ratio is 1/2 again. So the infinite sum, as I'm sure everybody knows, is like a upon 1 minus r, and this is like half upon 1 minus half, and you already know that this cancels, so it's like 1. Okay, so you didn't get infinite number at the end, you get a finite number, and it's actually equal to the distance that was needed to be traversed. So yes, the idea that you have infinite numbers and they can be added to a finite number, this was not well defined at the time of Zeno, and that's why he ridiculed the idea of continuous motion. But now you understand that continuous time and space are just fine. Space are just fine. You can define them, right? They don't lead to any kind of paradox. And a simple way in which we see this is like that, right? So everything is all good. So let's come back to our basic assumptions. And Newton said that if this framework is holding up, then why shouldn't I define it? So he said that the space and time are continuous variables, right? They are continuous variables. The second assumption, to understand that, you can say, let's say for someone who has never thrown a ball, he is standing here on this 2D plane and he wants to throw this ball. And you already know, if you have studied elementary physics, that, or even natural sense will tell you, the angle at which you will throw the ball and the speed at which you will throw the ball actually changes the trajectory of the ball, or the way in which it will move, right? If you throw it at this angle, then it will be a different kind of trajectory. If you throw it at this angle, it would be different kind of trajectory. And if you throw it at a very high speed, it would be a different thing. So actually, the initial velocity as well as the initial angle is needed. They are needed, right? Because every time you change these parameters, you can see that the trajectory of the ball changes. So what Newton said was that for defining motion in general, you need some initial parameters. Some initial parameters are needed to predict the motion of particle or the motion of object, right? So you need these things, some kind of initial object. And further on, we will see that the number of initial parameters is actually 2. And this has to do with the fact that the motion is a second order differential equation. But we will come back to it later on when we will discuss the Newton's laws. Okay. Some other assumptions are again needed. He said that time is universal. And what does it mean? What does it mean? It means that, let's say you have a clock A, right? This is your clock, and you have a clock B. And this is your guy A. This, assume that this is you. You have this clock in your hand, and this is your friend who's like, let's say his name is B, and he has this clock as well. And let's say you both have agreed that at some point, like let's say when I blow a whistle, or you guys have pre-agreed upon some kind of arrangement, at that point you both will activate your clocks. So at that point, your clocks will start ticking. And the way in which this universality of time can be understood is the synchronization of all clocks. Synchronization of all clocks. And by synchronization, I meant that, let's say you have this guy A and this guy B, and they both open up here their, or they switch on their clock at the same instant of time. Then every 2 seconds, let's say, after every 2 seconds, the hands of these clocks are moving together, right? They are synchronized, they are in sync. So what he said was, it doesn't matter whether you are here or at moon, and let's say you guys are saying that the train will come at 6 o'clock, and it's 5:55 right now. Then the amount of time that will take, 5 minutes to be more precise, for this guy here and this guy here will be same. Okay, it will be same. It means that both of your clocks are in sync. It doesn't matter whether you are here or at the moon, the amount of time or the interval of time will be same, right? So this was the idea of universality of time. And let's try to write it in more clearer way, that given to observers, or that two observers who have synchronized their clocks will always agree about the time of an event. About the time of an event. Right? Now, what is an event? You will ask. But for now, you understand this, that if you have two guys and they have synchronized their clocks, then they will always agree. They will always agree about the time of an event. And we will define what the time is, or the event is. Okay. Let's do that right away. And let's see what an event is. And an event is a very simple way to describe it. Let's see, you have again a bird. Okay, I will just write bird because I'm not that good at drawing. And this bird is flying. And this bird, and if you want to say, okay, this bird was, and this is like a very, what can I say, a very evolved bird or something, and you want to describe it to your friend, and you say, okay, I spotted this bird at 6 o'clock at this position. Okay, so what you are trying to say is you are defining some parameters. You are trying to define some parameters which your friend can relate. So you are definitely trying to describe time, so the time at which you saw it, and the position at which you saw it. And this is a point in space. And for Euclidean geometry, you can say that this can be defined by x, y, and z, a three-dimensional space. Right? So if you define the time as well as the space coordinate, then you have defined an event. So an event can be defined as just these four coordinates. If you describe these four coordinates, you're describing an event. Describe the four coordinates. Okay. So this was it, just the definition of event. Now all of this, and now of course Newton assumed that the geometry in which he is playing with all of these things is Euclidean. He assumed that geometry is Euclidean. Okay, and I assume that everybody knows Euclidean geometry, what it is. It's basically defining the XYZ coordinates. Okay. So, and again, the last assumption which we will say is, he said that there is no limit. There is no limit on your accuracy of observing, what can I say, of measurement. Okay, so the way in which you will measure, there is no limit to this accuracy, and this will actually come back to quantum as happens in quantum mechanics. But for now, this is the groundwork that you need to understand, that for Newtonian mechanics, the very, very basic principles are that space and time are continuous, and that some initial parameters are always needed to predict the motion of an object, that you have this universality of time, that if you have two persons which have synchronized their clocks, they will always agree about the time of an event, and then there is no accuracy to the measurement, right? And there is no limit to your accuracy of an measurement, and then the geometry is Euclidean. Okay, so we will come back with more topics later on, and we will try to discuss this in a much more thorough way. Okay, so I hope you stay tuned. Thank you.